Welcome, everybody in the lecture hall. Welcome, everybody following us on Zoom. Welcome, everybody from the future watching the recordings. My name is Gislain Fourny. I'm passionate about databases. I'm also passionate about mathematics. And this semester, I will introduce you to the world of relational databases. More generic term would be information systems. And I hope that at the end of the semester, I will have transmitted some passion to you. The goal is that you can also use these technologies for semester projects, for master's thesis, as a better way to store and manage your data than just programming with Python. And so I will show you all the tips and tricks, best practices, the math, the models, and we'll explore this together in the next 14 weeks. Today is a bit special because that's the first day, so it's an introduction. I will not dive as much in the material as in the coming weeks, but I still thought the introduction from previous years was a bit boring, so I removed a few slides and made it a bit shorter, and maybe we can even start a bit with the relational model today. So we'll see. So how do I introduce this? Well, I like to say that data scientists, you might have heard of data science, has become a bit of a buzzword to the point that we even have a data science master's program at ETH. I think it's a bit like physics. So I will a bit explain why, but one of the ways to see that is that when you manipulate data, you manipulate molecules and atoms of data. And just in the same way you can assemble atoms into molecules, quarks into, with electrons into atoms and so on, then you can also create beautiful databases with atoms of data. So we'll see how. And the way I compare it to other sciences is that they are the sciences that have been there for thousands of years, mathematics, physics, mainly as fundamental. What's the difference between mathematics and physics? When one of the way you could see that is you can do mathematics from your armchair at home and just think about numbers, math, axioms, and so on. But physics, you cannot do a priori from home. You have to go out there, you have to build experiments, and you have to see the results of the experiments. That's because the universe is what it is. It could have been different. The only way to tell is to experiment and see what happens. Now, other people might disagree, or there's a lot of physicists, theoretical physicists, that can do a lot of things from home, but that came later. That's because we discovered that mathematics itself can also be useful to understanding the universe. And then came the computers. So this is a bit more recent. Now we have a whole discipline of computer science with the departments that were created in many universities, mostly in the 80s. Contrary to what many people think, computer science is not just about sitting in front of the computer and program. It's a lot of theory as well, the theory of computation. It was actually a bachelor's course just before us this morning. That's a lot of theory. So it's also the sort of things you can do in front of a blackboard. In fact, there are plenty of researchers in the computer science department that only use their computers for writing emails and for writing papers. Right, so that's pretty common. And then there's data science, excuse me. And so I put data science right below physics because in a way, data science is also about experimenting and looking at how the world is. And that's actually something you can take literally because the picture that you saw on the cover of the lecture, hi Marcin. Marcin is going to moderate the lecture. So if you raise your hand, you ask questions also on Zoom, he will interrupt me and you should feel free to do that at any time. So if you go to CERN, who heard of the Higgs boson, the discovery? Many of you, right? It was front news. Well, it's not like the physicists just sit at CERN in front of the collider and look and, oh, here's a Higgs boson. That's not how it works. In fact, what they do is that they gather the data. They run the collisions with all the particles, and then they gather petabytes of data, gigantic amounts of data, and then they look at the data and process it and find the Higgs boson in the data with statistical tools and so on, like standard deviations, sigmas. All right, so literally, data science is a bit like physics in that sense, that you discover the world with the data, and like computer science because we use computers to do that because it's so much faster. And there's good wisdoms from thousands of years ago by Plato that you cannot just rely on numbers, you also have to base yourself on knowledge. And this is what database systems bring you. Information systems turn data into knowledge. But before we dive into what we'll do this semester, I like to start with a historical perspective, a short historical perspective. So we'll start with the prehistory of data. So you know, for normal prehistory, history is the invention of writing, right? But for databases, I would say it's 1970 marks the start of the history. So I'm not going to start recently, actually way back, thousands of years, where humanity started settling down. We didn't have computers back then. So how did we pass information? Well, there were people, it was almost their job, right, to speak and sing, and they would just travel everywhere, and they would tell everybody the stories of what was happening and what the kings and queens were doing and so on. And the information would propagate like this. They would speak, they would sing. The knowledge would also propagate through families or from people to people, just speaking with each other. But as you can imagine, that can be quite slow, much slower than today, where you know within a second what's happening in the world, but back then it took time. Plus, people make mistakes, people forget, right? So there's a lot of issues with this. And so there was a revolution, the invention of writing, where our ancestors figured out that you can actually use some symbols and mark them durably on some support, and then it's going to survive thousands of years. And in fact, this is when we started having insights into what happened back then, because that survived literally thousands of years and reached us. So we haven't decoded everything, but a lot of them we actually know how to decode. That's the Rosetta Stone. It's 3 times the same thing in different languages, and this is how we managed to decipher some of these languages. Some of them we still can't. AI is helping, so AI managed to decode some of them, so maybe it will also figure out some others. But this is text. That's not the only thing that people did in writing back then. And the next slide is my favorite of the entire lecture because it just gives me the goosebumps to look at this. This is thousands of years old. That is a relational table on a clay tablet. Columns, rows, exactly like spreadsheets as we have today, or the way we store the data. What does that tell us? It tells us that table representations, are very intuitive to human beings. In fact, it's even more intuitive than pie charts, scattered plots, and so on. All the visuals you can have, everybody understands tables. So this is why it's no surprise that this actually gave rise to the format in which we have many of our databases today. What's stored in there is Pythagoras triples. You know, like in a right triangle, the square of the largest side is the sum of the squares of the other two, right? That's Pythagoras theorem. And these are sets of integer triples that can be size of a right triangle. There's a few typos in there that we fixed today. So you can see that on a clay tablet, you cannot just press delete, right? You really have to start all over again if you make a mistake, right? So this is a bit challenging. But we still had a problem, that's the copying. If we have some information stored on a clay tablet, or even on paper later, that came later, we need to copy it over and to make it known to more people. So for many centuries, that was actually typically the work, for example, in Europe of the monks, who would just spend their days copying and copying and copying over, but that doesn't scale. And the real scaling of the copying of information was the invention of the printing press. Right? This is when we figured out a way to make thousands and millions of copies of the same thing, just by using what we literally call in German Buchstaben, right? So these are the letters. You just assemble them somewhere, and then you just use ink in order to just make plenty of copies. So that dates back to I think the 16th century with Gutenberg, and that was a revolution, culminated in the 19th century in the golden age of the printed press that even became daily with the daily newspapers. Thanks to the printing press. Of course, we had more technologies like the rotatives that made it even more efficient. But you see, it progresses. Then we had computers, but they only came later. What did computers bring us? Acceleration. We could do that faster and faster and faster. First mechanical, just with mechanically moving parts, and then with silicon and the transistor and the miniaturization. What's incredible to think of when you look at a picture like that is that the power of this computer is less than the smartphone you have in your pocket. It's less than your smartphone. Plus, when you switched it on, the electricity would just go out in the entire city because it was so power consuming. So you can see all the progress that we've done there. So we managed to accelerate. And now we find ourselves in the 1960s, where we can store the data on drives, and we have file systems with directories and files, as you have them on your laptop. And back then, this is how people queried their data, right? They store the files, and then they write programs. It wasn't Python back then. It was like COBOL, Fortran, other programming languages. And they wrote the programs to read the data, to write back the data, and just manage the data. But it was very complex, very, very complex, and it was a lot of efforts to do. And this is when the revolution happened. With Edgar Code in 1970, this is Edgar Code, he had a brilliant idea. He thought, since tables are so natural to everybody, we should expose the database as a table to people, and people should only ever think of tables. That's it. All the rest should be completely hidden from them. You would have engineers that implement everything to make it work on the file system, but all the users just should deal with tables that everybody understands. So that was the revolution, and the idea is called data independence. And I'm going to be repeating data independence all over the place the entire semester, so you can expect that at the end you will understand data independence, the separation between the logical and the physical level. And so he did that with tables. Of course, we'll see there's other shapes, but originally that's the relational era. I'll explain why we call it relational relation. That I will explain to you why a table is like that, has to do with math. And then things continued to evolve. You might have heard of C++, Java, so that was all the object-oriented languages that appeared in the 80s and 90s. So that was the object era, and some people tried to bind their databases to these things, to the languages. Then in the 90s, that was the business analytics era, where startups were created in order to analyze cubes of data. We'll see them at the end of this course, at the end of the year. And the startups were then bought by the database companies, and now they each have theirs. So they each have their own system for data cubes. Very popular for sales data and for the C-level executives in a company to manage the company. Then in the 2000s, what happened is that there was so much data, and here I'm thinking of companies like Google, Yahoo, Twitter, Facebook back then, who just had so much data that it was breaking everything. So they had to come up with new systems. We'll not study them during this lecture. That would be big data for engineers. But we have key-value stores that became a buzzword, just like blockchain or AI back then. Everybody wanted a key-value stores. It was incredible, even if they didn't need one, but everybody wanted one. Then we have the column stores, triple stores, that's the graphs and document stores, like you might have heard of MongoDB. All right. But this, not in this course. That's just the cool things that happened a bit more recently. Which brings us to the topic of the lecture. We'll focus on databases. Machine learning is not in the lecture. AI is not in the lecture, but it's all connected. Because in fact, you can see a relational table as the machine learning data sets, where the columns are the features and the labels and so on. So in fact, it is very related to machine learning. So if you take machine learning lecture and a relational database lecture, or maybe also big data for engineers, then you have the whole ecosystem to prepare the data for use with machine learning and then AI. I also tell you how AI relates, like LLMs, to this, right? The data information knowledge wisdom, probably this comes from some consultancy company like McKinsey or BCG, I don't know, but it's a very popular way of looking at the hierarchy of information, right? So data is really a raw thing. Then you extract information, and then you get knowledge, wisdom. So I have several courses that I offer. This is information systems for engineers. There is big data for the master students only in fall, big data for engineers, which is the same course, but for all departments. And so information systems for engineers, big data for engineers is for everybody from all departments at ETH who want to learn about these things with various backgrounds. Speaking of which, I'd like to know what your main background is. I'm trying, I just discovered it last week when ETH purchased the license for everybody, so I hope it's going to work. You're supposed to go to menti.com in your browser and to type that code. And normally, this should move. There should be data that appears in here, if everything is working. And I'll use that a bit during the course. Yeah, it's working. We have a lot of mechanical engineers. MAFT, it's the biggest bachelor's curriculum, I think, of ETH, MAFT, the most popular one. So a lot of mechanical engineers, mathematicians, physicists, not from the armchair, from the lab, ETH. Awesome. So that gives me a bit of an idea. By the way, this works in the lecture hall and on Zoom. That's also what makes it nice across the two locations. All right. Okay, so that you see, there's people from all over ETH, and that means that you shouldn't hesitate to ask questions, because I know you don't have all the knowledge that we have in the bachelors of computer science. So I'm here to explain. All right, so this is something you should not hesitate. Both in the lecture hall and on Zoom. You can even, in Zoom, you can write in the chat, and then Marcin has the authorization to just interrupt me, and I will answer, right? Okay. This is the TA team. So you already know Marcin. There are other TAs, Panos, Denitz, you, Marcin, another Marcin, and Yisong. Actually, some of them here. Yes, yes. All right, so come to the front. Come to the front. Oh, okay. So this is Alexa, and he's going to be also. So thank you for coming and for being with us. I will add your picture as well. Send it to me, and I'll add it. All right, and Marcin and Alexa. All right, all right. So, what are we going to do? We are going to look at the relational model. That's the math behind everything. Then we are going to look at something that's called SQL. It's a language that we use to create data, to query data. We're going to look at the relational algebra. That's basically the math that allows us to manipulate tables. We are going to use SQL to query these tables, and then we'll get into the scary part with more theory. That's going to be database design theory, indices, how to make databases super fast, architecture and storage, and then data cubes. That's the business analytics part, and then an outlook towards big data. All right. So what is expected from you is that you attend the lecture. It's best in the lecture hall because it's more fun to be here together, but Zoom works as well. You have the exercise session that's going to take place. So there's multiple groups that the TAs have, but not in the first week. So there's nothing today, and on Monday it's going to start the Friday after that, right? And then there is the written exam that's 3 hours in the winter session. Which will give you 4 credits. So that's the idea, right? Don't be scared of the 3 hours. We really try to give you something that is doable in less, but we give you the time so that you have time to think and double check your answers. All right? Yes? The exam is going to be on computers. Yeah, that's going to be, but not BYD. That's on ETH computers. So it will be either in the main building here or in the ONA building in Earlycon. Yeah. Mm-hmm. All right, thank you for asking. And of course, I'll tell you more about the exam as we go. But since it's ETH computer, you don't have to worry about making your computer works, right? So if there's any issue with the computer, we just move you to another computer, and that's it. What it means on a computer is that we use Moodle, so it's a Moodle quiz. That's a lot of multiple choice questions, or you need to enter answers. You'll have also a database system installed on the machine, and then you'll be asked to use it and run some queries and answer some questions on the machine. But it will just work. That will be pre-installed on the machine. All right. Next, we have a chat server hosted at ETH that can be used for interaction within the team and with everybody else. And you can connect there, and we'll invite you to the room of the lecture. We also have a Moodle forum in the Moodle, and then the TA team will let you know which way it goes. All right. The material will be available in Moodle. So this is the address right here. It should also be linked normally from the course catalog. But this is where you will find all the slides, all of the exercises, and everything. All right. Okay. So now we are going to start diving a little bit into concepts on the high level and see how far we go. So what is data? Well, it's something, we'll define that something, facts about the world, that can be stored and that can be exchanged. Stored means that you can put them in there on your computer drive, on your machines. Exchange means that you can also send them over the wire. Like the data goes over this, and then you can send them from machine to machine. So that means you can download data sets from the internet, you can upload them, and you can store them on your machine or in the cloud and process them. Now there is a whole hierarchy that's this data information knowledge. Another way to put it is that data is a bit like wheat, you know, that is in a very raw form. And then you do something with it and process it and get derived data information. And then you transform it into knowledge. That's when you start applying it and making decisions based on that, right? So it's very abstract, again, like consultancy slides, but again, we'll get very, very concrete. And so an information system, in the sense of the ones we'll study in this course, is a system, an ecosystem around data and information that manipulates information. It stores it, it manages it, it makes it accessible to you, you can interact with it. So that is an information system. What kind of data can you have? So let's explore a little bit. So first, the data, the oldest that you can imagine, would be just text, right? So that's very unstructured. It's just like what we write in terms of words. You have pictures. When it's digitalized, technically a picture is just pixels, right? You just have the color information of every pixel that you have in the picture. The pixel is just an atom of the picture. It's a little square. And then that gives you a picture. If you use the all versions of Windows or that kind of operating system, you might know that a picture is also referred to as a bitmap. That just means that it's bits in the end. It's zeros and ones, and it's a huge matrix with the color information of every point, right? So this is also considered unstructured. We have audio, the sort of things when you listen to Spotify or any other place. That's also unstructured data. And you have videos, which you can see as sequences of images, of bitmaps, plus the audio on top. The paradox is, this is what we've had for, well, this forever, this took a bit more time, and this took a bit more time. And in spite of this being very old, that was also the most challenging ever to deal with computers. Because it's unstructured, there is no structure in there. We humans look at it and see something, but it's very hard to make a computer actually see that because it's very raw. And what's incredible, and now we are in 2025, and this is something I could not even say in 2021 because that appeared in 2022, ChatGPT, where now you can do that. You can take text, pictures, audio, videos, and you can interact with a system that's able to understand them, to generate them. So these are very, very exciting times for us, that even that kind of data now can be dealt with. And what's more, it's pure math. It's all based on linear algebra and vectors. So if you're wondering who goes to a linear algebra class or took one? Many of you, right? So if you ever wonder what's that useful for, well, it's useful for ChatGPT and many machine learning, artificial intelligence. It's all based on that. Scalar products all over the place. Which brings us to structured data that unlike the unstructured data has a bit of organization in there. That's an example. Actually, it comes from ChatGPT because ChatGPT can also give me that. So I quickly asked it to generate some table that I can show you. And what you can see here is rows and columns, basically. It's the most populous countries in the world. So you have rows, you have columns, and this is a relational table, like the one we had on the clay tablet, right? So columns and rows. So this is fully structured. And this is the world of relational databases that we will study. And also, if you use spreadsheet software like Excel, LibreOffice, FreeOffice, and so on, these are all the same shape of data, structured data. It's a bit older than ChatGPT. And what's incredible about it is that turned the man into the richest man in the world, relational databases. So just to see how a big deal it is to use relational databases. That happened just last week. There was a sudden surge with Oracle that was one of the first companies to implement relational databases. And then there's in between. In between is what we call semi-structured data, where we have XML, JSON, data frames you might have heard of with pandas. And so, who heard pandas? Right? So we'll also put it in perspective. We did in big data for engineers. It's a little bit like relational tables, but it can break a few rules that I'll tell you about. All right. So this is what we call semi-structured. What does that mean? We have a whole spectrum, right? That goes all the way from fully unstructured, so the kind of things you use ChatGPT or LLMs to process, and goes all the way. There's graphs, trees, tables, and cubes, the business analytics. So this is unstructured, semi-structured, structured. And in this lecture, we'll focus on this, on the tables and cubes. So in order to do that, when you want to deal with data, the first thing you need, and that's also true if you design a language or anything, you need a model. So on the very high level, a model is whatever is a useful tool to look at the world, right? You have physics model, you recognize the equation? Schrödinger, right? Quantum physics. Maps, there's geographic information systems, also a model of the world. You have literally models that you can hold in your hands that are some replication of the world at different scales, economic models, and so on and so on. And we have the relational data model with that kind of fancy diagrams that you can see in many companies. Who has ever seen something like this? Right? So some of you. So when you're in a company and you want to build a system, then you need business analysts who come up with the entire documentation. And so when you want to prepare a database, then typically you produce documents like that tell you what there's going to be in your database. In that case, it's stuff that you sell. So these are the things you sell. They are called parts. These are the suppliers that give you the parts. There's the customer information. So you see some key, a name, an address, a country, a phone, and so on and so on. So that's basically a relational model. Looks very scary, so we are not going to so much look at them in this form. Rather, we'll look at table, but this is how it looks like. It's not the only one. In fact, there's also a data cube model for business analytics, large language models. It's also called a model, right? When you have text, images, and so on. Then you have models for XML and JSON when the data is a bit arborescent. That's not part of this course. And also models for the graphs that is also not part of this course. Okay? So these are models, and we'll explore that. We'll spend 1 or 2 full weeks exploring the relational model, and with a bit of luck, we might even start today. Where do we have information systems? In universities, in supermarkets, banks, social networks, newspapers are databases, flight booking systems, geographic information systems, online stores like Digitech, Amazon, and so on. So Google is an information system. So that there's a whole lot of them. In fact, that's why it's so massive, is that I think it would be very difficult to find any company in the world of a certain size that does not have an information system or relational, specifically a relational database. It evolves actually very quickly. I mean, you might have seen these graphs. It's generated every couple of years. I haven't found the latest one, so I took the 2021. But that tells us how much data we keep generating just as we use the internet, all the data that gets generated. So it's massive amounts, probably now largely in the yottabytes category what we produce. In fact, there's a rule of thumb that basically says that in the past few years, we've generated as much data as since the beginning of humankind, just to see how exponentially it's increasing. And what I'm saying about the past few years was true 2 years ago, was true 3 years ago. It's always true. You look at the past years, as much data as since the beginning of humankind. That's enormous. And so that brings us to also another thing you find on consultants' slides, the 3 V's of big data. Who has heard about this? Okay. So we have volume, variety, and velocity. So I'm going to start with volume. Volume is the idea that we're kind of running out of prefixes to say how much data we have. I'm assuming that probably most of you know all the way to here. Is that fair? Okay, who knows this? Who didn't know it before? Okay, so now you know. This is how it continues. And in fact, the story is very funny because it used to stop here. So this is all standardized by as the international system of unit. You can use it with meters, with grams, with bytes, with anything you want. And it stopped here. And then some physicists run out of prefixes in their papers, and they say, okay, Z, Y, so let's call it X, W, and so on. And so they started writing things with X and W as prefixes. Didn't make it into the standard, but it led the standardization body to add a few of them. And so Rona and Quetta are more recent. That is just a few years ago. So now we have it with 27 and 30 zeros, Rona and Quetta. I think their main use case was to express the weight of Jupiter, the mass of Jupiter that didn't have enough, that had too many zeros. And so now with this, we can express the mass of Jupiter. Okay. Since I'm a computer scientist, I could not resist, and I had to show you this, because you know that computer scientists love powers of 2, and so you might have heard that when a computer scientist says 1,000 or kilo, they actually mean 1,024, because that's 2 to the power of 10, 2 times 2 times 2 times 2. And so it was a bit of a mess, because then nobody understood anymore if you really mean 1,000 or 1,024. And so the standardization body also decided to standardize that, but they gave them different names. So they say Kibi, maybe, Gibi, and so on. And that's it's not Pokemon, it's actual prefixes for the powers of 2. And of course, I'm not expecting anybody to learn this by heart. Maybe 1,024 you can know, but no other expectations. It's actually fun that the coincidence that 2 to the power of 10 is almost 10 to the power of 3, right? Because that approximates all of these powers of 10, every 3 zeros. You just have 10 to the power of 10, 20, 30. It's just a coincidence that it's working like that. Even though when you go down, it starts deviating a bit, right? Because now it's 1.2 and not just, yeah. All right, so that's the international system. Now, what is also characterizing an information system is the front end. is the fact that you have a website somewhere that interacts with you with HTML that you might have heard. That's the page that you see. But behind this, hidden, there is an information system. There is often a relational database management system. And all what you see on the page, here, the price and so on, that all comes from a database system behind. And after this course, you will know what it looks like, all of the way that this is stored. And you'll also know why it's so fast, because if you think of it, how can it be that you search on Amazon or Digitech, you press enter and it's immediate. You immediately see the results. That's quite impressive, right? And so you will understand why. So now, why do we need that in the first place? Because you might think, and actually a lot of people do it like this today, why don't we just put the data on the disk and use Python to query it, right? It's very tempting to just go ahead and do that, very popular. And I'll try to make you understand why that's an idea that doesn't scale. And that can be a bit cumbersome. It's good to hack around a little bit and do a few things, but then in a professional environment or in a production environment, that's just not what you can do. So imagine that we do that. We have a company with 1,000 people and they all deal with their data like that. They store it as files on the disk and then they use Python in order to interact with it. Then very quickly what you'll notice is that everybody is going to have their own. Everybody on their computer will have their own data on the disk and they'll have their own programs. So HR will have the payroll data, there's going to be the inventory, people that have the orders, then the products, the stock, the inventory, so all kinds of databases for this. And it's going to become a bit of a mess if you don't pay attention to this. And so one issue that you could have is redundancy. Maybe there's going to be the same data stored on multiple places in multiple databases. And then that's a problem because if you fix it, if you modify it at some place, then you might not modify it at some other place. And then it's inconsistent. So you might get some inconsistency between the machines. So you see a lot of challenges start popping up. And what if you want to combine the data? You have the data that is stored on some laptop and the data stored on another laptop. What do you do if you want to combine it? Right? And we'll see in databases, we love to combine data. This is what we call a join. So that's also challenging. So this is why people started building information systems, database management systems, and Edgar Code actually was the one who pushed for this. So I have a top 5, like they do on TV, you know. So 5, you enforce integrity constraints. That means that you make sure that your database is in a healthy state. For example, you might have, if you're a bank, that the balances are positive. You might want, for example, that the number of students registered for this class is not a negative number, you know, these sort of things. And so a system can enforce that. It will not let you put any data that doesn't fulfill the constraints. Second, you can support multiple users, 10 users, 100 users, 1,000 users, 10,000 users, 100,000 users. As you can imagine, with Python, you cannot do that. Imagine if everybody is connecting to your laptop and writing Python remotely at the same time on your disk, that's going to break your machine. That's not going to work, right? But the database systems, they are able to deal with thousands, hundreds of thousands of people connecting to it and using it, right? So that's another thing. Number 3, avoid the data loss. Who has ever lost their data because the drive broke? Usually in every room, there are people, it happens. By the way, reminder, back up your data if you haven't backed it up, especially student projects and so on. It can happen at any time that your computer can break. And for this reason, in a database management system, you have systems to back up the data, avoid loss. You can store it redundantly at multiple places, so it's taken care of. Then you can have access control, because if you are a very large company with hundreds of thousands of people, you want to make sure that anybody can read or write specific places, right? So for example, at ETH, students cannot just connect to the HR database or, you know, and see everything, right? So this is, and even I cannot do that. So there's access control and people need authorization, and a database management system, an information system does that. It decides who accesses what. And finally, that saves you a lot of development costs, right, as a company. Instead of just building something yourself, you can just use an existing piece of software that already exists. The big companies, probably they will take Oracle, IBM, Microsoft, the big three, maybe SAP. But there's also free and open source pieces of software available, like PostgreSQL is free, MySQL is free, so there's plenty out there that are free. So that really saves you costs, especially, for example, if you're a startup or you start, you try to found something, then that really helps to have all of this available. Okay, I'm just checking the time. Oh, we still have a few minutes before the break. So now that we have these systems, what are they made of? So there is something that I'll explain in deeper details in a few weeks that's called the 3-tier architecture. In any website, when you go to a search on DuckDuckGo, or if you want to order something from an online shop, this is likely to look like this. So the easy part is the user interface. That's the website. You're in your browser, you see the page that appears here. Then you have the business logic. That is something intermediate. That's a lot of computer codes that processes and tries to understand what you want to do, and then it connects to the database. And the real database, so where it is there's a persistency layer that deals with writing the data and reading the data, and the data is actually right here, right, on your drive. And so you often have these 3 layers. So if I caricature a little bit, this is the website, the HTML page, CSS, JavaScript. This is going to be Java, C++, JavaScript, server-side, Python. And this is going to be SQL and the database management system, right? So these are the 3 layers that we'll get into. And so now what's really nice is that now I slightly modified the slide using these 3 layers, the persistency, business logic, and the front end. And now what we do is, instead of having the drives like this, we just replace that with a single place, a database. It might be multiple computers, but a single place where we store the data, and everybody just connects to that place centrally. Right. So that's what we call a database. A database, in fact, is the data itself. When you say database, you don't mean a system or a program, you just mean the data. The program is called, so there's drives, of course, here, but they are not directly accessible. They are just somewhere on the servers. The piece of software that you download when you download PostgreSQL, as we will do during this lecture, that's called the Database Management System. That is the software that manages the data. DBMS is very often used as an abbreviation for Database Management System, so you shouldn't be surprised. And the two together, database plus Database Management System, is what we call a database system. So you should know these 3 by heart, what they mean. The database is the data, the Database Management System is a piece of software, and the database system is the whole of it. That's the ecosystem. Okay? It's a source of confusion very often. You will hear a lot of people that call PostgreSQL a database, but PostgreSQL is a DBMS. It's not a database. And that's what we are going to focus on. It's going to soon be the break, so I'm going to stop here. And I'll see you in 15 minutes, and then we'll continue the lecture from here. Thank you very much.